Alkali-Silica Reactivity, or ASR for short, is one of the major causes of cracking in concrete. To put it simply, a gel-like material forms when moisture causes a chemical reaction between alkalis in the cement and silica in the aggregate. As the gel expands, pressure causes the concrete to crack. In this program, we'll take a look at ASR determination, prevention, and testing, both new and conventional. The new testing is largely attributed to the research conducted by SHRP. So, let's get started. Determination. As you know, cracking in concrete can be caused by a number of factors. Fortunately, the types of cracks and their locations can give you a good indication of the specific cause. In addition, evidence of the gel-like material is a sure indication of ASR. If you suspect ASR, the first thing you should do is review the Handbook for the Identification of Alkali-Silica Reactivity in Highway Structures. In it, you'll find detailed descriptions of crack patterns normally associated with ASR. By comparing the pictures to the actual cracks, you can see if you need to investigate more closely. Okay, that's determination. Now let's look at prevention. Many of the problems associated with ASR can be prevented by paying close attention to the materials, namely selection and pre-approval testing. Low-alkali cements, for example, can be helpful in many instances. These cements are defined by ASHTO as having no more than 0.6% alkali. The use of low-alkali cement alone, however, may not be enough to prevent ASR. Alkalis can also be found in certain types of aggregates, notably volcanic aggregate in the western United States. As a result, alkalis can become concentrated in the concrete by wetting and drying cycles. They may also be derived from such sources as seawater and de-icing salts. Pozzolanic materials are widely used to prevent ASR. These include fly ashes, ground granulated blast furnace slags, and silica fume. Fly ashes are most effective when they replace 20 to 40% of the cement. Slags are used at higher quantities, replacing 50 to 75%. Because silica fume is very finely divided and reactive, it's normally added in the range of 5 to 10% by weight of cement. You have to be careful, though, to test each particular cement pozzolan aggregate combination before using it. That's because all pozzolans of a given class are not equally effective. ASTM C 441 can be used to evaluate these materials. With the wide variety of materials and combinations of materials available, it's easy to see why careful testing is crucial. Testing is the only way to ensure satisfactory performance when there's any question of potential alkali-silica reactivity. With that in mind, let's look at a couple of new tests. The first one, gel recognition, is so new it doesn't even have a designation yet. The second one, ASTM P 214, involves quick detection of ASR. We'll start naturally with gel recognition. As I indicated earlier, the presence of the ASR gel is indisputable evidence that ASR has developed. Many times this is only detectable by a skilled petrographer using a laboratory-grade microscope. But now, as a result of SHRP research, field personnel can recognize this evidence much earlier in the life of the structure. To use this method, you will need the following items: a source of short wavelength UV light and viewing box, uranyl acetate solution, distilled water, 2 types of protective eyewear, conventional and UV absorbing, rubber gloves, and a hammer or other surface preparation equipment. The first step is to carefully study the safety information in your user's manual. The uranyl acetate solution can cause serious injury if it's not handled properly. You should also know that residue produced by this test is a hazardous waste, so be sure to study your state's regulations for this too. Best results are obtained on newly formed surfaces. These can be created by breaking off a piece of the concrete using a hammer, grinding off concrete to expose a fresh surface, or taking a core and washing off drilling fines to expose a fresh, clean surface. Fracture surfaces, such as those produced by a hammer, are preferred. Then, the specimen is rinsed under tap water to remove any residue, and the surface is blotted dry. Protective eyewear and rubber gloves must be worn for the next step. The uranyl acetate solution, prepared according to the instructions found in your user's manual, is sprayed onto the fresh surface. Only a small amount of the solution is needed. The specimen is allowed to stand for 5 minutes. Then the surface is rinsed with water. The wash water is allowed to evaporate, and the remaining powder is retained, but cannot be used to make new solution. Before observing the sample, put on the UV protective glasses. Then, put the specimen inside the box and turn on the light. The ASR gel will be revealed by a yellowish-green fluorescent glow. Deposits of the gel will be localized in cracks, air voids, and around and in certain aggregate particles. If sawed or cored surfaces were used, there may be smearing of some of the gel, which is why it's better to use fractured surfaces for the test. For further details on interpretation of the test and some good examples, refer to the SHRP handbook for the identification of alkali-silica reactivity in highway structures. And that brings us to the next test, ASTM designation P214. This test was initially developed in South Africa, further developed in Canada, refined by SHRP, and proposed to ASTM in 1990. The official title of the test is Proposed Test Method for Accelerated Detection of Potentially Deleterious Expansion of Mortar Bars Due to Alkali-Silica Reaction. The major benefit of using this test is that results can be obtained in as little as 16 days, as compared to many months using conventional testing. The material to be evaluated must be in the form of a fine aggregate having a particular gradation. So you'll have to crush coarse aggregate to use this test. Fine and crushed coarse aggregate are then dry sieved to obtain the size fraction needed to make the gradation called for in the method. Next, the sieved material is washed and dried. And each portion is stored individually until the specimens are to be prepared. The materials for the batch are then weighed out in the proportions called for by the method. They're mixed in a standard laboratory mortar mixer as described in ASHTO T162. Be sure to add sufficient water to the mix to get a fixed water to cement ratio of 5/10. The molds used to cast specimens for this test have dimensions of 1 by 1 by 11 1/4 inches. The molds are fitted with gauge studs in order to accurately measure the length changes during the test. After coating the inside of the molds with release agent, the mortar is cast into the molds in 2 layers, consolidating each layer with a tamper. The molds are placed in a moist cabinet for 24 hours. The specimens are then carefully removed from their molds, and an initial length is recorded on each specimen. Next, special containers resistant to heat and hot alkali solutions are filled with tap water, and the specimens are placed inside. Be sure the specimens are completely immersed. Now the containers can be covered with tight-fitting lids to prevent evaporation and placed in an oven for 24 hours. During this time, the temperature has to be kept at 176 degrees Fahrenheit or 80 degrees Celsius. Now the specimens are removed one at a time from the containers and a length measurement is taken. This must be done quickly because the specimens cool rapidly once they're removed from the water. After each specimen is measured, it's placed back into the container. Then the water is poured out of the container, and a 1 normal sodium hydroxide solution preheated to 176 degrees Fahrenheit or 80 degrees Celsius is poured into the container to cover the specimens. Remember that this solution is dangerous. Always wear protective equipment when preparing and using this solution. The containers are then placed back into the oven. The measurement process is repeated 3 times during a 14-day period. At the end of the period, the average expansion of 3 specimens is calculated. If the average expansion exceeds 0.1%, there's a potential for deleterious expansion. Less than 0.1% indicates an acceptable aggregate. It is expected that further refinements may be made in the method before final adoption by ASTM and AASHTO. This may include revisions in criteria, as well as its use to determine the maximum alkali level in any given cement aggregate combination. It may also be possible to eventually use the method for testing of actual concrete specimens. Further information will be available in final publications from SHRP. And that covers the new tests. Now let's look at 2 conventional tests, ASTM C227 and ASTM C289. But before we get to the details, you should know that although agencies have used these tests for many years, both have considerable limitations. For example, C227 fails to identify many slowly reactive rock types, such as granite gneiss and quartzite. And it often identifies reactive aggregates as harmless due to the fineness of the sample and fails to identify an acceptable alkali level. With that in mind, let's look first at ASTM C227, Standard Test Method for Potential Reactivity of Cement Aggregate Combinations, Mortar Bar Method. Aggregate samples for this test method are prepared in an identical manner to those used for P214. The mortar is then proportioned from the crushed and graded aggregate in a similar manner, except that a flow test value of 105 to 120 is used rather than the fixed water to cement ratio. As in P214, the molds are placed in moist storage for 24 hours. Then they're carefully stripped from the molds, and an initial length reading is obtained. You'll need special containers and racks to store the specimens. The containers are made of heavy plastic and are fitted with blotter paper. The racks are also fitted with blotter paper, and the spacing in the frame serves to prevent the specimens from contacting each other or the paper. When assembled, the blotter paper will wick up water from the bottom of the container to help keep the specimens moist. Further, the containers are sealed with tape to prevent loss of water during the test. The containers are stored inside an environmental room for 14 days. During this period, the temperature has to be maintained at 100 degrees Fahrenheit or 38 degrees Celsius. Then they're taken out of the room and allowed to cool. After cooling, the specimens are removed from the containers and their lengths are measured on a comparator. Only in the case of very reactive materials are the readings taken at 14 days, useful in predicting reactivity. If expansions are not observed over the initial 14-day period, the specimens can be placed back into the containers and measured at later ages. Testing can continue up to and beyond 1 year in some instances. For long-term testing, the larger containers shown here may be more appropriate. That's because a lot of alkali may be leached from the specimens if they're left in the smaller containers for long periods of time. The aggregate is generally considered reactive if expansion exceeds 0.05% at 3 months or 0.1% after 6 months. And that brings us to the last test, ASTM C 289. Formally, this test is titled Standard Test Method for Potential Reactivity of Aggregates. The material to be evaluated must pass the number 50 and be retained on the number 100 sieve. To obtain this size fraction, the as-received material is initially processed by passing through a jaw crusher. The crushed material is then sieved to obtain the desired sizes. The sample is then washed, dried at 105 degrees Celsius, plus or minus 5 degrees, and inspected. If any particles are found to contain silt or clay, the sample must be re-washed. The crushed samples are then weighed into stainless steel containers. Sodium hydroxide is added. The lids are secured in place. And they're placed in a heating bath for 24 hours. During this period, the water temperature must be kept at 80 degrees Celsius. The containers are cooled under running tap water. Then, the liquid is vacuum filtered through a crucible. Now, the solids are removed from the container and packed into the filter. The filtration continues until only 1 drop of liquid passes every 10 seconds. A portion of the liquid passing through the filter is analyzed for dissolved silica using either a gravimetric or photometric method. The details are found in the ASTM method. The quantity of dissolved silica determined by either of these methods is termed S sub C. Another portion of the liquid is placed in a flask and titrated to an endpoint with phenolphthalein. The titration is complete when the liquid turns clear. The reduction in alkalinity is then calculated. This is termed R sub C. The test results are interpreted using this chart. The points for S sub C and R sub C are plotted onto the chart, and the region into which they fall is noted. Aggregates where test results lie in the potentially deleterious region may actually give only low expansions in concrete. These aggregates should be tested further by one or more of the methods you've already seen. You should also know that results of the test may not be correct if the aggregates contain carbonates or dolomites. In many cases, the test fails to identify materials that react slowly. For these reasons, don't rely on this test unless it indicates a very high degree of reactivity. Alkali-silica reactivity is a serious problem. However, By carefully testing, using standard and newly developed techniques, you should now be able to better identify those aggregates which are potentially reactive and take the proper steps to ensure long-term durability of your concrete.